And I think we can move to the next presentation about AI integration. So we're going to discuss artificial intelligence in space cybersecurity resilience, and specifically the hard question of what really makes it from a research lab into an operational satellite. So it's a little bit the same question we had with CCSDLS, but applied to this new AI techniques. So to talk about this, let me introduce Dr. Michael Felderer. He's director of the Institute of Software Technology at DLR, the German aerospace agency, where his team is one of Europe's most prolific producers of research on AI, testing and resilience for safety and security critical software. So he walked us through what works, what doesn't, and what's still stuck in the lab. Please welcome Michael.
Thank you very much. Is this now my laptop, right? Okay. Yeah, thanks for the kind introduction. My name is Michael Felderer. I'm the director of the Institute of Software Technology at German Aerospace Center. So I'm actually the head of a research institute in German Aerospace Center. DLR is a bit broader. It also is an agency and it also has operational facilities. But I'm from the research branch. And the talk that I give today is a bit an overview talk. Actually, originally it was supposed to be in the other track, but then it was shifted to this one. And I'm happy to give you an overview on an AI-enabled cyber resilience for space system and also what it needs to move on in this area. So first, I see here in analogy to the three-body problem of space, three-topic problem that we have to deal with, and that makes the problem a bit specific in this domain of space, namely space systems themselves. I mean, you all know they are limited in their resources. They have very severe physical constraints, and this is something that makes the application of AI, in particular on board, very, very special. Yeah, limited availability and so on. And then cyber resilience brings in another dimension. Cyber resiliency requires redundancy, it requires deep understanding of assets, and bringing these worlds together is actually a challenge that needs to be addressed from several perspectives, right? So space systems, as you all know, this is a slide that I normally use when I talk to non-experts, is a topic that becomes now very prominent. Space systems are complex cyber-physical systems of systems, right? And AI plays a role in the system in many respects. So, I mean, AI, on the one hand, it brings in several opportunities. The first one that might even have been used in the use case that we have seen before, I don't know in detail, is that for sure when developing a space system, then AI provides you additional assistance for the development of the system. Maybe dealing with requirements, maybe dealing with testing, even implementation. So there is a high potential for the application of AI. The second aspect for sure is AI has not only the potential to improve the processes for designing and even operating space systems, but also AI-based applications have high potential. Common use cases here are, for instance, Earth observation, where you can do onboard AI-based pre-processing, right, which may reduce the amount of data that needs to be transferred, for instance, that allows you more powerful onboard applications than before. And the third one is AI in operations, and in particular also AI to support cyber resiliency. So one area we are working on, but I've also seen here that companies are working on this, is anomaly detection in AI-based mode, right? You can use the features of AI, like pattern recognition, to actually identify anomalies and to deal with them in various respects. So the topic of AI in the space domain also has a momentum. I mean, I see it as an editor of the SEA Space Journal that many submissions come in that address this topic. So we see an actually exponential increase. And also industrial cases like concrete satellites show that with a onboard AI show that this is significantly increasing, but also the subtopic of AI-enabled cyber resilience in this context is increasing. And yeah, there are many things ongoing, but there needs to be this link between the pure digital and the operational world to make big steps forward, and I want to provide you a few ideas on this in my talk. Yeah, so let's discuss this topic of AI as an AI for cyber resiliency a bit more in detail. I mean, there are also several perspectives on that. So for sure, the first one is that AI is here a defensive accelerator. I mean, you can use AI both on ground and on board for anomaly detection, pattern recognition, attack fault correlation, warnings, and prioritization of alerts, right? There are many solutions around already. So that is for the ground segment already established. For onboard, it's becoming actually, given the specific constraints that you have there, now and more important topic to come up with solutions there. The value of AI here, also that's important, is not replacing operators. It shortens, but the key point is that it shortens the time between anomaly detection, understanding, and action. I think that's the key point of the application of AI in this context that also needs to be made explicit. For sure, there are always two coins, two sides of the coins. AI, on the other hand, is also a multiplier for attack surfaces. So it opens additional potential attacks. I mean, many of them are well known, but they for sure also hold in the space domain, maybe data poisoning, model drift. The models do not adapt properly to the actual change in the situation. Model manipulation, but also a high false positive rate may be an issue, and adversarial inputs that might be there, or safety real-time guarantees that needs to be taken into account. So in space systems, AI errors are not, that's also important to state, and that makes it also special in this domain. AI errors are not just classification errors, as maybe when you classify images, right? Examples that we all know, but in the space domain, they can become mission errors, and therefore the application of AI needs to be solidly backed up with resiliency mechanisms. And the third perspective that has become more prominent recently with Mythos from Anthropic is that AI may also be an offensive tool, right? So this is something we do not yet fully understand, even in more well-established security domains. Yeah? But this may also be for sure become a critical issue for the space domain. However, at the moment, there are, according at least to my knowledge, And as I heard also from the threat intelligence report yesterday, no confirmed AI attacks on satellites, but for sure there is an indication that AI can enhance the attack path against space ground segments, cloud infrastructures, suppliers, and mission operators. So in general, resiliency, the space systems are always safety critical, and cybersecurity introduces a bit a trade-off that we have to deal with. So there is always the tension between classical safety engineering and cybersecurity engineering. I mean, I want to make this obvious by some aspects. So, I mean, for sure, when you, for instance, go for safety critical software, then you have to deal with legacy code, which you often exactly do not replace because of safety issues. And this might, on the other hand, be a very critical point for intrusion detection systems, right? Because for them it's tough to deal with that. Yeah? On the other hand, intrusion detection systems might block safety critical processes. Then there is also an issue between reliability of safety critical applications and intrusion detection systems, which might compromise the reliability due to false positives rates, and also redundancy that you want to bring into space systems via inversion programming opens new issues, for instance, with respect to extended supply chains, which are then also have to deal with potential supply chain attacks. So I now opened several perspectives on the topic, and in the remainder of this talk, I want to present some directions we are actually working with. If you want to discuss some of them in more detail, then come back to me, and we can do so. So the first one is that we really, if you want to deal with cybersecurity properly, even in the research context, we need to take the different layers into account. So we cannot only do things in a lab mode. So considering AI models in isolation, right? We need solid verification and validation environments that also consider the hardware in the loop already. And we need even to integrate the operational perspective, even already in the research perspective. So that's one point that makes this a very tough area to integrate this perspective. So AI for space cybersecurity cannot be validated solely in laboratory conditions. It must be evaluated across mission representative environments to ensure trustworthy operation in orbit. And this is also exactly what we are now tackle. There is this gap between the industry-ready products that are operated and the fundamental research that is available at universities. For instance, with respect to cryptography or AI-related resilience methods evaluated purely in a lab environment. And what we really need is in between this high-fidelity research that takes hardware in the loop, software in the loop, powerful, high-fidelity digital twins into account. And what do we mean by that? We mean by that that we need hardware in the loop facilities, software in the loop, scenario engines, digital twins, and operational cyber resilience and orchestrated knowledge transfer. And in particular also training in terms of red and blue teaming. So before I just want to pitch a concept of a space cyber range that we actually address, I also want to show you what we actually do content-wise in the area of space cybersecurity. So we have built and validated an app store concept for space systems. We call it Stellar Apps. It's an onboard platform, but also a development model, which has the following layout. So hardware, operating system, communication day, application day, and then different apps that we can deploy. The apps that we actually use here are coming from partners within German Aerospace Center, which also does work, for instance, on robotics, Earth observation, and so on, right? And from that, different apps come into play that we position on the Stellar Apps platform. The onboard data analysis, real-time information, automated telemetry, health monitoring, satellite attitude estimation, tracking, computational sensing for onboard inference and compression, and so on. And we soon launch this in orbit in our DLR Captain CubeSat mission. In the development of the security concepts for Stellar Apps, we adopted the attack fault tree approach, right? So I guess many of you know attack trees and fault trees. Fault trees come from a traditional safety engineering, right, where you try to come up with potential faults and their impact on the safety of the system. And the similar concept are attack trees for potential attacks. And you see here one of the example, access to radio frequency update transmission, bypass of telecommand authentication. So if this happens in this sequence, then injection of a malicious telecommands over radio frequency uplink is possible, and this might lead to a violation of telecommand integrity on the radio frequency uplink. And this issue, this failure may result in the failure of the telecommand integrity on the radio frequency uplink. And here you have then the classical fault tree, right? The fault could also come from another issue, not only from security, but we in particular are interested in the impact of attacks in this context, then the resulting failure and the final failure to control the attitude of the spacecraft, right? Yeah, so what have we done in our Stellar Apps platform? I told you it's not only the platform itself, right, the onboard platform, but it's also it comes with a development and deployment process. So also with application development environment with a ground interface and then respective uploads to the space segment. And here we have integrated respective vulnerability analysis during development and also identification of hardware-specific bugs. So it's always essential to take both worlds into account. And in the space registry, we have an authentication via public key. Yeah, and then on the platform, right? So we have here different nodes, so where the apps can actually then be deployed, and an app manager, and each Stellar app, right, on the Stellar Apps platform is running in a container engine and itself within a container where we actually have isolation for it and also respective contracting for its behavior. Yeah, and finally we also have a dedicated integrated security layer that we are actually developing when we are exploring AI capabilities. So in this security layer we consider access control, message authorization, and also intrusion detection, right? Based on AI. So the AI thing is something that we are currently exploring here. Yeah, and finally we are actually moving towards the concept of a space cyber range that actually allows so first the blue teaming the high fidelity based research with powerful digital twins to actually secure systems during design, and to later also enable red teaming with the mission to not only detect, to not only be able to answer the question, was an attack actually detected, but also to answer, was mission loss prevented or mitigated under realistic constraints in this environment. So thank you very much for your attention.
Thank you very much. Do you have any questions on this very interesting topic? Yes.
Hi there. Thank you for a very interesting talk. Are you planning to make your your software a bit more available?
So that's thanks for the questions. Yeah, actually, we are already. I mean, for sure, we have developed, evaluated, and use it internally in DLR. But we are already in exchange with external. With companies like OHB, right, to use it in that context. But we do not plan to make it entirely open source, if you mean that question. But we are open to collaborate and to license it.
Any question? Yeah.
Thank you very much for this very interesting presentation. The implementation of onboard security, onboard spacecraft, always imply very strict swap constraints. Does this carry the risk of making the system predictable for an attacker because of the swap constraints?
Yeah, so we, you mean for predictable for the attacker?
Yeah, so because of the use of AI, and it will necessarily imply some resource constraints on board.
Right.
Some researchers have highlighted that this might be a threat, because a vulnerability or risk, because it could imply that they can guess how the system works.
Yeah, I mean, this is something we are actually exploring. So I mean, for us, onboard AI-based anomaly detection is still a research topic where we explore which real added value it provides compared to let's say more classical pattern recognition approaches. So that's actually something we're exploring, and where I do not, and you also have to take trade-offs into account, right? When does this onboard AI anomaly detection really make sense from a resource perspective versus the added value that you have? So actually, for us, this is an actual research topic we are working on, where I cannot come up with a final conclusion yet. Yeah.
And I have another question. Did you use a specific framework for your research, for instance, Sparta, to explore some threat scenarios targeting onboard systems?
We use such. I mean, we use approaches to actually model our threats and to have an overview, but we are not yet. I mean, we are more, let's say, not in an operational environment yet. So we do not do it in a fully systematic way, I would say. So we are exploring specific approaches. We take the tough ones and try to deal with them. Yeah.
Thank you very much. Very interesting presentation.
Thank you very much.
Anyone? If not, I just have a question on my side. So do you have any non-deterministic algorithms in your stack, in the stack you presented? And we were talking about compliance this morning, how European will enforce more and more compliance regulation there. Do you see any issue in adopting these type of technologies on board?
I mean, if you have some parallel and distributed system, you to some extent always have some non-determinism. So that yes, that definitely is the case. But these are mechanisms for actually handling also resiliency, right? We are still in a, as I said, in a more research mode. We want to actually investigate which impacts these things have and bring them back exactly to this compliance standards and regulations. That's also the role that we have in the ecosystem.
Okay, thank you very much. Thank you for your time. And so we have a short break now of 30 minutes.